So we are not supposed to hit the decomposition zone. Always effort should be to make sure that we never hit the decomposition zone, come what may, hook or crook. And the fifth is wherein straight away once cooling failure happens, it just enters a decomposition zone and decomposition happens. So this is a worst case. So this is the increasing order of criticality. Higher, since as you go in the x direction, x-axis, you will see the more critical situations in the far right and less critical situations in the far left. So this is a very famous classification. You better use this classification also for yourself, because you will know how safe you are or how unsafe you are. Okay, so what exactly calorimeter does is, again I want to reiterate, what reaction calorimeter does is, you will be able to know, because you know anyway TP, it will be able to give you MTSR values. And because you know the boiling point, once you use adiabatic calorimeter or DSC or thermal screening unit to get this decomposition range, this graph is complete. And based on that, you will be able to design your safe process. So generate reaction calorimeter data, get delta T adiabatic, get MTSR values, you know the boiling point, get the decomposition data using preferably adiabatic calorimeter, if not the DSC, and then complete the social chart. Clear, friends? Very important point I told you. In case you have any questions, you ask right now so that I can clarify. Please, it's a very, very important point I mentioned, important points I mentioned. Please ask any kinds of questions you have at this stage. I can move on. If at all you want me to move on, I will. Okay, good. So next is, I want you to, very, very crucial chart. I want you to understand this Semenov plots. Yeah, so before, as I move the slides, I want to tell you, see, there is one question about, like, you know, TMR, TD, TMR 24, TMR 8, TMR 24, and people have lots of questions, you know, what is this TMR? You know, I'll tell you, again, you have to listen very carefully, because a very, very critical and important concept, and many people miss out on this. TMR is nothing but time to maximum rate, or time you have to go to a situation where your process is running away. So when you say TMR of 8, that means you are having 8 hours of time before your process runs away from you. In the sense, you have only 8 hours of time. And that temperature, suppose say TMR 8 is say 120 degrees. That means once you reach 120 degrees centigrade, you have only 8 hours of time for your process to run away when you have no utility or no cooling happening from around. And TMR 24 is nothing but the time you have, the temperature at which you have 24 hours of further time before your process goes to run away. See, your processes, once a reaction, normal reaction happens, as any typical chemistry, there is going to be small incremental reaction rate that is always going to be there. And that will result in a slight temperature range slowly. And at 24, TMR 24 means at that particular temperature, you leave the reaction like that by closing everything and not allowing heat to be removed or heat to be absorbed. will run on its own by having incremental temperature rise within based on the self heat or the heat that is liberated from within the mass. It will be grabbed by the process mass, and it will start having a temperature rise, and ultimately it will go to the temperature wherein it will run away from it. So TMR 24 means that is a temperature value at which you will have still 24 hours of time when you have perfect adiabatic conditions. And TMR 8 means you have only 8 hours of time. So once, and if at all it is TMR 2, means you have only 2 hours of time. That means आप TMR 2 तक पहुंच गए. Once you reach TMR 2, that means you don't have any time. Your process is running away from you. Come what may, you are going to have dangers. So that is the reason why we try to use these values, either TMR 8 or TMR 24 or TMR 16 or whatever, so that we manage our normal reactions, so that we never hit TMR 24. And TMR 24 or TD 24, it is same. TMR 24 means TMR means time to maximum rate. TMR 24 means you have 24 hours of time to reach the maximum rate. And what is that? It is nothing but the temperature from which it will take another 24 hours. Clear? I hope the concept is clear. If at all it is clear, you say yes or you give a thumbs up. If at all you didn't, then again tell once more. It's a very, very important concept. Okay, so it's a temperature. Somebody is raising the hands. Yeah, I can actually put in the chat box. Yeah, so here is a Semenoff plot. See, Semenoff plot is no. Here we are talking about concepts of decomposition only. Okay, you are asking me to give one example, Abhishek. I'll talk about it later. Okay, let's quickly talk about Semenoff plot. Semenoff plot is see, you have a heat data with respect to temperature. A typical normal reaction, say, assume when you are having higher temperature, your reaction rate is going to be higher. Based on the Arrhenius equation, that rate of reaction is nothing but A e power minus Ea by RT into your concentration of ingredient reagent. So your K is nothing but Ae power minus Ea by RT, which is your Arrhenius rate equation. And as the temperature increases, that the K value increases also. That for every 10 degrees centigrade, the thumb rule in your college, you are chemical engineers or physical chemists here, they know that the rate constant gets doubled, right? You guys know. So here is that. Now what happens is that here you look into when this is nothing but your utility temperature. So what happens is that once your utility gets in contact with the heat, this is also heat that's liberated from the reaction. Your process is controlled. In the sense, your utility temperature, the inlet temperature is less, or the utility, because you are having a glycomic reaction, and this is the utility temperature, and if it is less, and this is the utility graph, and the slope of which is your UA. You know that Q is equal to UA into delta T. You know that, right? I mean, you have heard about it. I actually showed it a few slides back. So Q is equal to UA delta T. So this slope of this line is UA. So once this line hits it, that means your reaction is under control. But once you keep on increasing the utility temperature, a point comes wherein this line just becomes a tangent to this Q curve. This is the reaction heat curve. That means you are able to just manage. And if the further utility temperature is raised, there is no way this utility temperature is good enough to cut this line. If at all it is not cutting this line, that means your utility is not capable of controlling your reaction. That means your reaction will just run away from you. In fact, it is a famous Semenoff plot which was developed by Semenoff, and it was in fact used for designing nuclear reactors. In fact, this came much before your reaction calorimeter invention itself. This is actually in the early 20th century, but more or less the concept is same only. You can use this for design purposes. I'll tell one more thing. Here you see, when you go to the next slide, you have this heat curve, and what I also can do is I have a lower UA, and when I keep on increasing UA is nothing but a combination of overall heat transfer coefficient and surface area of heat transfer. If area of heat transfer is increasing, because for a particular typical reactor system, you can't increase U, you can keep on increasing A. And when you keep on increasing A, slope increases. So once area is increased, you see, there is a point at which it is cutting the line. That means there is a minimum area that you require sometimes to control your heat of reaction. So not only that, you have to have utility temperature proper to control your reactions, you need to have enough surface area to control your reactions. In laboratory, surface area per unit volume is very high. In your pilot plant, surface area per unit volume is high. But when you go to commercial reactors, surface area per unit volume gets reduced. So you will not have enough area to manage reactions. And that is where what we saw with reactions with excellent control in laboratory are no more controlled beautifully on plant scale. The dangers which you don't see at all in lab, you tend to see on plant commercial scale. That is because of this. So I am just trying to show to simple Semenoff plot how you can actually understand. So you not only have to look into areas, you have to look into your temperature of utilities for designing your systems for safe processes on commercial operating facility. Guys, clear? So if at all it's clear, give a thumbs up. Or if at all you didn't, I'll explain. Wonderful. Okay, so now let us look into this slide. Now this slide is what I was talking about. Here you see, this is the temperature axis, right? And this is the time axis. When you are having, this is the process temperature on the left hand side, and once you have a reaction happening and there is an adiabatic situation, the maximum temperature it will go up to is MTSR. And if MTSR is less than the decomposition range, no problems for you. This is the decomposition range. If MTSR crosses, it enters this region, that is where the problem is. And this is your TMR. As I told you, this is the time you have. So if at all you have 24 hours of time and MTSR is reached and you still have TMR of 24, then you are safe. In case it is not that, you have to figure out what you need to do with your processes. Clear? Okay. So this is the pictorial graph of understanding MTSR and decomposition temperature range. Okay, I will quickly talk about a case study, which is important case study. We are running out of time. I'll try to do very fast. See, there's a case study which is in fact a case. This is actually happened in one of the companies. There is a halogenation reaction wherein halogen is dumped in a vessel, and then heating is started. So if you see, I mean, this is the material dumping. You see the purple color of the material is dumped, and after it is dumped, the heating is started here. And one particular point at which, at one particular temperature, heat is suddenly released. And this is huge amount of heat that is released. So what is happening is the complete material, whatever is here, it is dumped. And then after dumping, you are just increasing the temperature, and obviously at one particular temperature, the normal reaction is triggered off. But are you checking whether you are having enough utility? Are you checking the right utility with you? Are you checking whether you have surface area? No, that's a problem. So what happens is that if you don't do this, it is actually going to be dangerous. I'll tell you exactly the situation, the hazards. So the batch size was 200 kg. The solvent was cyclohexane. You had a heat of reaction of 190,500, so 1,90,500 kilojoules. And the process temperature is 50 degrees. So for this heat, what I was talking, the delta T adiabatic was 180 degrees. So the MTSR was 130. Okay. So 130 degree MTSR, and you are talking about cyclohexane, which boils at around 80 degree. So what's going to happen? You are going to have very bad consequences. You are going to have huge pressurization. You are going to have solvent loss. You are going to have pressurization which actually can go up to 40-50 bar, because the pressure increase is going to be so high that will fundamentally explode your reactor. So what else can we do? In order to manage the hazards, imagine there's a situation. I think there's one of the guys also, as I see, I think Srikanth, he is actually the guy who has also worked in this process. So he knows a bit or two. He's one of the, I think one of the delegates, as I see here. Here you see the reaction, the addition of the halogen is done slowly here. So you go to the conditions at which the temperature is happening, and go to the temperature at which reaction is happening. There's operating temperature, and then once you go to the operating temperature, right from the gram 1 of addition of halogen, you will have the heat release that's happening. And then you keep on adding, and you keep on controlling the heat, and you see to that the temperature rise doesn't happen that much, and it's under control. This is a temperature rise. And by the amount you complete, by the time you add it completely, you are left with a very small amount of residual heat. This is the total heat, and what you are left with is a very small amount of residual heat. I am telling you guys, whenever you are managing your reactions, you have to make sure that your residual heat is as minimal as possible. That is the most important thumb rule for managing hazardous reactions. Let us understand what happens when we change the situation. The process temperature is 50 degrees centigrade, which is a batch process dumping process. When we convert it into a semi-batch process, the process temperature is same 50 degree. But in case of the previous case, or in previous case, the adiabatic temperature rise was 80. Now in the present case, the delta T adiabatic is only 8 degree. because you are left with only small amount of residual heat, and that will, even though if cooling failure happens, the temperature rise will be only 8 degree. Okay, and so here MTSR is 130. Your residual temperature rise or adiabatic temperature only, or residual MTSR is 130. Now the new temperature reaction, final temperature with the residual heat is only 58 degrees. So 58 degrees centigrade is much less than the boiling point of cyclohexane. You have overcome that problem or that dangers of pressure increase and explosion and fire and possible detonation, deflagration, detonation, etc. Okay. Earlier, what was the situation? In order to control this heat, people were using minus 20 degrees centigrade brine. Now, what exactly you can do? You not to control heat at 50 degrees centigrade, you can manage with CT water also. So I am telling you guys, many a time, in order to manage processes safely, you can manage processes safely in a very simple way. You can get simple solutions. And I am telling you, if you are smart enough, you can get cost-effective solutions as well. Minus 20 brine, yeah. I mean, it's basically economically, like, it's not infeasible for you guys because you are managing businesses and pharma industries. It is not cost-effective. Whereas if at all you're talking about CT water, you're definitely saving money because you're talking about day in and day out of utilizing the same utility instead of minus 20 brine. So we have a distinct and definite advantage here. Okay. You guys, what I suggest is find the optimal process temperature with the help of kinetic data along with process data information. Please convert your batch process to semi-batch process in a very smart way. If at all it is possible to tweak the temperature here and there, you can work around. Even if at all it's required to discuss with your development team, also discuss, figure out what is the best way you can do, and convert your batch process to semi-batch process, and then actually make sure that, like, you save utility, right? Find out ways of reducing your delta T residual adiabatic temperature rise, and find out ways of reducing the process operating cost. Sorry, and then you can make the process more economical. So when you're talking about safety, don't think about safety comes at a cost. Please understand, safety is nothing but figuring out ways of getting information and using the information so effectively, so smartly, that you can make a better life for yourself 360 degrees. I'm not saying that this is going to work for all the cases, but I'm telling you, most of the cases, it's going to be like that. Okay. So I will quickly move around because we don't have much time. Because we have only 15 minutes time. I'll talk about a kind of I'll talk about a case study here. You are able to see the slides? Shalini?
Yes, sir.
Are you able to see the slide only?
Yes, sir. Only slides.
Okay. Okay. This is slide number 93. Yes. Slide number 92. This is the mixed acid nitration reaction, wherein you must be knowing a compound by the name metronidazole. People from pharma industry know about this. Metronidazole
still we are on 76 number slide, na? It is not changing. I think you are saying 90 some reaction, but it is showing the plot.
No, now it is 90.
I don't know, but on my, maybe there is some network issue on my end.
No, people are seeing 90. People are seeing 90.
Okay, then it is fine.
Yeah, fine. Okay. So 90 slide, yeah, you're able to see 90 slide. See, this is actually reaction about metronidazole. Metronidazole is an anti-protozoal drug. It is developed, it is synthesized from imidazole. There's a nitration reaction. So what you're doing is glyoxal, you convert to a compound called methylimidazole, and methylimidazole is through nitration converted to methyl nitroimidazole, and then later on converted to metronidazole. There was a case wherein people were thinking that they can manage the nitration reaction beautifully. For years together, they were managing one particular time, and the nitration reaction is very tricky. They were having a kind of a closed loop heat exchanger system, and they were very happy, wonderfully well operated, and continuously methylimidazole is pumped, nitric acid is pumped. There's a static mixture through which actual reaction happens, and the cooling also happens beautifully. But there is once a heat exchanger failure that had happened. It required actually a immediate cutoff of nitric acid also. But what happened on the fateful day? There was a loss, or the cutoff didn't happen. Nitration was happening so fast that it resulted in the total destruction of the plant. It happened in India. Okay. I want to talk about critical case studies. The next I want to talk about the Grignard reaction. Alkyl halide, when it reacts with magnesium, it gets converted to alkyl magnesium halide. Okay. And then later on, you use this reagent for further processing. Okay. So the formation of this alkyl magnesium halide is very crucial. If at all you don't have this reaction appropriately happening, you tend to have runaway scenarios. Most of these Grignard reactions are conducted using tetrahydrofuran as a solvent, and it boils at 66 degrees. So people keep adding alkyl halide, magnesium turnings are there inside the reactor, and they'll keep on adding alkyl halide. Reaction didn't trigger off, they keep on adding, and they keep on adding, they keep on adding. I am telling you, there are many incidents happen on a commercial scale wherein people just were taking chances. They keep on adding alkyl halide, they go up to 20% addition, 30% addition, 40% addition, then boom, I'm telling you, it becomes dangerous. As of now, people are figuring out ways. There are ways wherein people have used intensified systems to make the process intrinsically safer or inherently safer. But Grignard reaction has its own dangers. It is one of the most dangerous reactions to be managed. I am telling you, people should not play or risk managing this Grignard reactions. Okay, so I have few more case studies, but I'll quickly skip through because I can share the presentation. So there are, because we have only 10 minutes time. So again, this is again quickly trying to give a concept of wherein, one question one person was asking, I just forgot the name. He was asking about thermal conversion and chemical conversion. So I want to tell you that if at all you are using reaction calorimeter appropriately in the right way, you will be able to use thermal kinetic data to design your reactors, and you can actually develop your own rate equations, and you can get the rate constants as well. In the sense, you can get K value, Arrhenius factor, you can get your activation energy, and you can actually get the order of the reaction also. and then use it for your reactor design calculations. So not only for safety but also for some other purposes. So that is one of the advantages you have for reaction calorimeters. You can use it for generating kinetic data also. Okay. So that's what I was mentioning. You can get E and A values. E is activation energy and A is Arrhenius factor. You can do that as well. Okay. I'll just quickly go through, go further. I'll talk about adiabatic calorimeter quickly. See, adiabatic calorimeter is something which got developed in the 18th century. People say that, late 1790s, 1780s, around that time itself, adiabatic calorimeter was there. So talking about adiabatic calorimeter, which is one of the most important calorimeters required for process industry, got invented or was used in 18th century, 19th century or 1820, 1830s. Whereas the reaction calorimeter came in 1980. So you can understand. It's ironical, but that's true. So adiabatic calorimeter, in adiabatic calorimeter, you do nothing. What you do is, this is in fact Ramal Hazard Technologies accelerating rate calorimeter. You take a bomb and inside this adiabatic unit, here it is basically the unit which makes sure that the whole thing is adiabatic. You put a bomb, close it, and keep on increasing the temperature, and then start seeing the magic, what happens. So the complete decomposition kinetics you will be able to understand, and that information you can use it for your process. So accelerating calorimeter is a perfect adiabatic calorimeter. So somebody was asking about phi. So phi is the factor which is used here. So pi is nothing but the total sigma of MCP divided by only M sample, C sample. So the total heat capacity of the bomb, including the mass, divided by the sample heat capacity is the pi value. You use this pi value for calculations, and then you can understand the realistic decomposition temperatures using that. It is just a correction which you can use. So again, I explained about this to you guys in the past graph. So what you can actually do is you can get information related to time to maximum rate. So that is what it is. So once you have the decomposition temperature ranges and the time to maximum rate, this information can be used further to design your system. So I was actually showing a social classification chart. In that, ATD24 is there. So you have a process temperature, you have MTSR, which is maximum temperature synthesis reaction. You have the properties of the mass, which is the boiling temperature and stuff. And then the missing piece is adiabatic temperature, decomposition temperature range that you can get using this adiabatic calorimeter. And if at all you use adiabatic calorimeter, the values you get are so accurate that you can blindly follow. And why? Because the information what you get from an adiabatic calorimeter is so accurate that it works for an adiabatic system perfectly. In the sense, you are talking about the data what you generate from this is applicable for a 100 meter cube to 200 meter cube reactor, which is handling highly hazardous exothermic reactions. 100 meter cube means what? 1 lakh liters. Whereas in case of your plants, you must be handling 5 KL, 20 KL, like that, right? I don't think you must be handling 200 meter or 100 meter cube, 200 meter cube reactors. I don't think so, right? So you are handling maybe 5,000 liters to 20,000 liters max, 25,000 liters, right? So when the data you get from adiabatic calorimeter is good enough to be used for 100 meter cube reactors, so you can you can easily use it for 5 meter cube reactors, 10 meter cube reactors, just by closing the eyes. So adiabatic calorimeter is definitely an advanced version of your DSC, but the advantage you have for DSC is you'll get a heat data, whereas in adiabatic calorimeter you will not be able to get straight heat data. because it works in the heat search mode. It keeps on heating, and whenever there is an exothermic event, it will try to track the exothermic event. That's what it is. So with that information, you will be able to get. So that's what I was telling you. I was talking about TMR values. So if TMR 8 hours, TMR 24 hours, or TD 24 hours is what is used. I already explained about that. This is how you will get actually the data in calorimeter. So in case there is any sudden temperature surge, you will come to know. Just like the way you are getting for TSQ, you will get. So this is the heat search wait mode. That's what it keeps searching. Once it sees a thermal event, it will allow it to run on its own. It will not heat any further. See here, the steps are indicating that some amount of heating is done by the instrument itself, the equipment itself. But once it searches and there is a heat event, it sees on its own, and the heat is self-heat, and it is actually going to heat the mass on its own, then it stop heating and allow the mass to get heated on its own, and then it track, and then it will convert into your TMR values, right? So, and then this data can be used. So once adiabatic calorimeter data is available for you, you can get a TDR values, and based on that, you can in fact decide how the process should run. In case if at all your MTSR is going into the TD decomposition temperature zone, you will have to accordingly tweak the process, or tell about the dangers of the process, or make sure that additional controls are there, such that the process is managed well. Okay. So, I mean, this is at a very high level about adiabatic temperature. So, I think Shalini.
Hello.
Yeah, Shalini.
Yeah.
Yes, it's 4 o'clock now. I think
yes.
The high-level concepts and very major level, I think we covered most of them till the adiabatic. So we have 50% of the sites still to be covered. Obviously, it's very difficult to cover in a single day, and all complete static electricity and dust explosion aspects have to be covered, and we have to discuss. So I think we'll leave for another day, or we'll have to plan a little bit differently for that. Okay, so shall we stop now?
Yes, sir. I think this topic we have just started now, thermal runaway and relief system design.
Yeah, I mean,
we have completed part 1.
Yeah, we have completed part 1. Yes.
Yes. Right.
We have completed.
Okay.
Yeah. I would like to just tell about a couple of slides. See, the thing is that, like friends, as I was telling you, I was also talking about Semenoff plots. This is a normal reaction. We talked the utility curve, how the reaction is controlled, and if at all the reaction is not controlled, it will go to a stage wherein there is going to be a runaway scenario, and there are going to be other secondary reactions also. So we are going to have, in case of thermal runaways, we need to worry about what is the kind of vapor release that's going to happen, and what are the gases that are released, because when decomposition happens, it is going to be a combination or a hybrid system which is going to be there. It's going to be a combination of vapor and gases. And so you need to make sure that you have to properly have relief systems for taking care of the releases. So what exactly happens is, when you are having a scenario wherein potential runaways are going to be there and you are ready to accept the runaway scenarios, what you have to do is you need to make sure that you create vents and relief systems such a way that you are not going to have any kind of explosion or disastrous consequences. What you're going to do is the relief systems itself are so good. These are all what you call as a protective measures. So what you're going to do is you're going to make sure that the protection systems are so good that even in case of worst case scenario, when you are having a huge release of vapors and gases, they will be taken out through vents, and the relief systems are so good that the vent sizing is going to take care of the releases. So this is what it is, and then it will make sure that, like, you have to calculate the area of the vent, what sort of area is required, and what sort of because the vapor has to escape at those conditions wherein you had actual runaway, and then you have to collect in a dike system wherein, like, you take it, you convert it to a knockout pot, and the further release of vapors is actually done through a flare or a scrubber, and you are going to take care of the potential uh, or potential runaway scenarios. When you have those potential runaway scenarios, you're going to still take care of that. Okay, so that is what it is. So when you are doing proper consequence analysis, you will take care of this as well. So quickly, I'll just give a summary. We talked about screening of process. So first we have a process, or you're carrying out process, or you're managing process. First of all, you look into the chemistry, figure out what exactly you have in the chemistry. You try to understand the higher hazard groups. Then look at oxygen balances and see if at all oxygen from within the molecules is going to be dangerous or not. Then you look at chemical compatibility aspects. You use software, you use various literature to understand that. Then you actually do your screening studies using DSC, and then try to understand the complete process, either in small steps or multiple steps, and understand the hazards through screening using DSC. Then you use other tools like the thermal screening unit or ARSST to get more accurate data related to temperature rises, pressure rises, and possibly the decomposition temperature ranges. Then you get into details of normal reactions, and then beautifully try to understand the normal reactions by using reaction calorimeter. The power, the heart of the process, or heart of process safety studies is reaction calorimetry studies. So use reaction calorimetry studies appropriately, generate wonderful data, because as I told, it's a heart. You can use that information so beautifully, not only to design safe process, but also to design optimal process and cost efficient and profitable process as well. And then go finally and look into adiabatic calorimeter for all these critical reactions. Study adiabatic calorimeter, do adiabatic calorimetry studies also, get the data, and manage your bad situations or potentially disastrous situations by designing proper relief systems and vents, so that, like, your organization doesn't get into problems. Okay, this is all in a nutshell. See, this process safety course in toto is a 6 months course. So we try to cover as much as possible at a very fundamental level, and covered most of the topics till you managing reactions. Okay, there's a lot more to it. We have a lot to learn about static electricity. We have a lot to know about static electricity in reactions. So I was supposed to discuss a lot of hazardous reactions like nitrations, fluorinations, diazotization reactions, Grignard and all. So those things, and then later on, all the dust explosion and water safety studies. We didn't have time, so we'll have to plan a little bit differently. Okay. So